Okay, so let me start. So today what I'm going to talk about is which I started last time, I guess, this single mode and two mode squeeze vacuum states. Okay, these details actually. Okay, so what I'll do is I'll talk about its um, wave function and then the Fock space representations. Okay. Uh, so the squeeze vacuum state, so let me call it as S1 of R because this is single mode squeezing, and I'm considering real squeezing. One can in principle do complex squeezing. So this is okay. What is this? This is exponential of. So the Hamiltonian is half xp plus px, and then I'll have to multiply by the amount of squeezing, which is R, and to make it unitary, okay, so this is my Hamiltonian for the squeezing. Okay, this is the amount of squeezing. So to make it unitary, let me take it like, let's say, iota, okay, or maybe minus iota. So this must be unitary, right? Because this is my Hermitian operator and this is a real number, so this as a whole will be Hermitian and minus I Hermitian operator. Okay, good. So this, if you calculate, it should turn out to be, what will be this? This should act on K0, yes. So this should turn out to be exponential of, so this part is what? So this should be R by 2, then a dagger square minus a square. I guess so, right? I mean, if you expand this x as iota, no, because this would be anti-Hermitian, okay. So this is a dagger plus a by root 2 and p is equal to iota a dagger minus a by root 2. Okay. Acting on 0, right. Single mode squeezing. Okay. As I said, this R can be complex, but for complex one I'll have to change it. Here it should be R, it should be R star, something like that. Okay. So what we want is, so this I already discussed, that if I want to write down its Fock space representation, it should be something like this, lambda 2n 2n, because no odd Fock states will appear here, right? So we'll have to figure out these coefficients. Okay. Now let us look at first its wave function. So this is so this is your position, which quadrature, which is dimensionless. Okay. So basically, these dimensionless position operators acting on x, it will give you x and x. So this is the eigenvalue equation. So this is one of R 0. If I want to calculate this, okay, right? Okay, so this, that this is S1 of R minus acting on x dagger 0, right? Because dagger of this is S1 of minus r. Okay. So I need to figure out what is this one. Okay. Okay, good. So now, in order to figure out what is this, so we take a detour. Yes. So this is your position representation of this single mode squeeze vacuum state. Okay. So in order to figure out this one, we take a detour. So what I do is, let me apply this position operator. Position means this is dimensionless on this state. Okay. Why am I applying this? I'll show you that basically this one is another position eigenstate. Okay. So this is, I can write S1 of minus r, then S1 of r x, S1 of minus r acting on x. Okay. Now this maybe I have done it already. What will be this one? This I think I have done, whether it is e to the power plus r x or e to the power minus r x. That is what I need confirmation. Okay. Otherwise we can do it again, but it will be just unnecessary wastage of time. It is e to the power r x, right? Plus r x, huh? Okay, good, good. So I take your word. So therefore, this is e to the power plus r, then S1 of minus r, then this is x acting on x. Is that correct? Okay. And now this is your just x. Okay. So e to the power plus r into x, and then S1 of minus r acting on x. Right? So you see that this position operator acting on this state gives rise to the same state with this eigenvalue.
The eigenvalue is e to the power r
into x
times x.
times x.
X is the number.
X is the number, eigenvalue of this operator. Okay. So this means that this is actually a position eigenstate, which, what is the position value? E to the power plus r times x. Is that clear? I mean, you can take a overall phase, but that is not an issue. Take an overall phase. Okay. Is it clear? Okay, good. Right. Okay. So let us look at once again here. So what we are looking at is x, S1 of r acting on 0. So this is basically e to the power plus r into x, then 0. Why?
Second last.
This one?
Second
This one? Why confusing?
Because I think the eigenvalue should be e to the power r times small x, right?
Why small x?
Eigenvalue of the operator x.
Yes, so this is a dimensionless operator. So that is why I have been denoting it by capital. Every time I am denoting it by capital.
Is also in capital.
Yes. This is operator, this is eigenvalue.
Oh, you have just written e to the power r x and taken it inside the kit.
Yes. This is a position eigenvector corresponding to this position. So is this clear? So therefore this is position representation of the vacuum state corresponding to this position. Is it clear? Okay. Now you look at, let me erase this part. Now you look at the position representation, let's say x prime of the vacuum state. Okay. What is this? This is, we know it will be Gaussian, and one can figure out. So I am not going to do that. You can verify. This is again dimensionless operator's position. So this will be 1 by pi to the power 1/4 exponential of minus half x prime square, where minus infinity x prime plus infinity. Okay. So this is the position wave function of vacuum state. This you can verify. There are several ways of doing it. You can apply this A operator on 0, it will give you 0, and then you take the position representation of that, and then you write this A as 1 upon root 2 x plus iota p, then acting on 0. So this is your 0, and then this is fine, and this you represent as minus iota and d dx. Okay.
This is same as the ground state wave function of the harmonic oscillator.
Yes. This is ground state wave function, but you'll have to keep it in mind that this is everything in the dimensionless position and dimensionless momentum.
Without h cross and 1.
Yes. H cross is 1, omega is 1, everything is. Yeah, so this is dimensionless. Okay. So if you do that, you will get this solution. Okay. So now this is x prime, can be anything. So what will be this? So this is a this is a position eigenvector. So this is normalized. Okay. Of course, in the Dirac delta notation, not Kronecker delta, Dirac delta. So can I write from there? So this is a question for you, because I know this thing. Can I write from there that this is pi by 4 exponential of minus half e to the power plus r into x whole square. Is that a correct way to write? Because that x prime can be anything. Yes? Think about it. What should be the criteria? Sorry?
You were just changing from x prime to e to the power r.
Right. But if I look at here, this wave function, is it a normalized wave function? In the sense that if I take minus infinity to plus infinity, dx prime, x prime 0 mod square, this has to be 1, right?
It must be like you have to do the Gaussian integral via the.
But this will be valid. You can do that and you can figure out this is the case. Okay. What about here?
Oh, okay.
You're not normalized, right?
I understood.
So what modification should I do here?
Okay, you have to change it, change your point.
Yeah. So what you should do is, take mod square of this, integrate from minus infinity to plus infinity, whatever value you get, take square root of that and divide this by that quantity. Okay. Right. So if you do that, what you will get is e to the power r by 2. I am not writing every time plus r because this is r. Okay. Is it clear? So this is the normalized position wave function of single mode squeeze vacuum state. And of course, this is Gaussian, like your ground state wave function. This is Gaussian.
R is a parameter now.
R is your squeezing parameter. Okay.
Okay, so the shape of the Gaussian will be intact, or I mean,
So what is the center of this Gaussian wave function? 0. And what will be the width?
it will be
Yes.
it will be
So therefore, as you increase R, width will decrease, right? Yes, it will decrease, which is expected. Okay. Okay, good. So
But there are two factors. Like one is e to the power r by 2
yes,
and one is exponential of, okay, leading exponential, so that will dominate.
yes.
It will increase the r.
No, I mean this Gaussian, you can figure out what is the width. Basically what is this? What is that called? Standard deviation or something. That you can figure out.
that is come in the 1 by something.
How
You can
they scale, because it will increase the r.
Yes, yes,
There is a prefactor which is e to the power r by 2
yes.
and there is another factor which is exponential of e to the power something. So that will dominate, I guess, and that's why you are saying that the width will squeeze.
Well, you can figure out. It is not so difficult. It is basically, if you take Gaussian, what is that called? The 1 by the standard Gaussian one is exponential of minus half. Yes, by sigma square, right? 2 sigma square, yeah. Then you will have to do the normalization here. Exactly, yeah. So this sigma square you will have to figure out. Okay. Yes, yes. So therefore, no, the sigma square will be your the standard deviation. Okay. That will be, sigma is the width. Yes. 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 R is fixed. Yes. Yeah, but my point is, if you increase R, what happens to the width? What happens to the? Exactly, exactly. Nothing else will change. Yes. Okay, good. So let me keep these two things here. This one and this one. X prime. So let me call it as X. What is the point of calling it X prime? S1 R 0. So this is e to the power r by 2, then pi to the power 1/4 exponential of minus half e to the power r times x whole square. Again, this is for so this is your for squeezed vacuum state. Okay, right. Yeah. Okay. So let me erase this part. Okay. So next, let us go to the two mode squeeze states. Okay, squeeze vacuum state. So which the corresponding squeezing operator, I will call it as S2 of R. S2 of R is exponential of minus iota. Then the corresponding Hamiltonian H2, I mean, of course, it should have R here. So this is, what was the case? I think it is R by 2 iota again, A dagger, B dagger, let's say AP. So this is my Hamiltonian. Okay. So therefore, this will be exponential of R by 2 A dagger, B dagger minus AB. So what I want is this one, S2R acting on 0, 0, because we are dealing with two mode case. Right? So basically what I want, because I am dealing with two mode case, so I'll write here XA and XB. These are the quadratures, position quadratures for the first mode and the second mode. Okay. So you want this quantity. Is it clear? Okay. So now
No, but how the I got vanished? Sorry.
no, this is your Hamiltonian. This iota r by 2 a dagger b dagger minus ab, right? This is your squeezing Hamiltonian corresponding to the squeezing r. And then you have already, because you'll have to have this exponentiate of minus iota times that Hamiltonian to make it unitary. Okay? Is it okay?
Yes.
And then this minus iota into iota is plus 1, right?
I mean, like the way you introduce the squeezing operator, squeezing unitary, that even in the single mode squeezing, you put a okay, a dagger square minus b square was there. Okay, right. Okay, sure.
Okay. So this is there is I mean this plus or minus, it is up to you what you take. Okay. So but once you fix your convention, let it be fixed everywhere. Okay. Right. So let us look at this quantity S2 of minus r, because if I take dagger of this, it will be S2 of minus r on XA comma XB. So I want this quantity. What is this? Right? So for that, what I can do is, let us apply this XA plus XB on S2 of minus r XA XB. Okay. And why I am applying this? It will become clear. Right. As in the earlier case, I want to see what is the effect of this action. Now this I think we have done earlier. What is this quantity? E to the power plus r or minus r, that is what we need to be careful. I mean, one can of course do it once again. So here S2 of r, S2 of r of these, and then S2 of minus r. So whether it will be e to the power plus r or minus r, that is what I need to get confirmation.
I think minus r.
Minus r? Anyway, this one can figure out. It's not. I think I have done it, but you can check it. So e to the power minus r, minus r. Then this is S2 of minus r, and then this is XA plus XB, and then this is XA XB, right? I guess so. Okay. So this is e to the power minus r XA plus XB. These are the eigenvalues. So XA operating on this, XA operating on XA comma XB, what will it give you? It will give you XA, XA comma XB, right? These are product states. And similarly, if I put it like B here, so it will be B. Okay. So therefore, XA plus XB acting on this will give you XA plus XB, and then it is S2 of minus r acting on XA comma XB. Is it okay? So, this quantity which is equal to this quantity basically turns out to be, no sorry, not this quantity, sorry. What I am doing is x a plus x b acting on this, okay, this quantity. This is what you are getting is this one, okay. So, what does it mean?
Which one?
So, you see x a plus x b acting on this state provides you this factor times the same state.
Eigenvalue equation. Right.
Yes. So, what can you say about the eigenvector?
Oh, so the eigenvector of the operator xa plus xb is this one, S2 minus
Okay.
So because xa plus xb is one operator and there is another operator xa minus xb and they both come with different this thing, e to the minus r1 and the other is e to the power plus r. Because of that we can't simply say that it's xa e to the power minus r comma xb e to the power minus r. We can't say that, right?
Yes. So, I'll this is correct. So, here let me take it also the with minus sign, and if I follow this thing, so here it is minus, I think it should be plus here, right? And here it is minus. So, here it is plus, here it is minus, okay, right. Now, what can I say?
Take the sum and say that
So, S2 acting on minus r xa comma xb, what can I write?
xa plus xb e to minus r
Uh-huh.
plus yeah plus so equation e to minus r xa plus xb then plus
Actually, I should have anyway, that is okay, that is fine. I mean, I should have put by square root of 2, then you will have a square root of 2 here.
okay.
I mean, just to normalize it, okay. So, I think that will be better, just to normalize it, okay. So, I should have put a square root of 2 here. Okay. So, if you put a square root of 2, ultimately you will have square root of 2, square root of 2, everywhere you will have square root of 2. So, this will be e to the power plus r, then xa minus xb by root 2. Is that a correct statement? So, is it an ad hoc statement or is it a correct one?
It seems ad hoc to me.
It seems ad hoc, okay, good. But you agree that, yes,
So this one is the eigenstate of that operator x a plus minus xb, right?
yes.
And you are expressing this eigenstate to be this one.
Yes,
So you are saying that whether this is valid or not.
yes.
So this is the answer in a specific basis, not in the original basis.
Yes. So, I will have to validate that this is indeed an eigenvector, right, of this operator.
Oh, then again you have to verify.
Yeah. So, this is, yes, I agree with Anupam, this is an ad hoc basis, okay. But up to this is clear, right, that this is what is going to happen. So, for this reason, to make things clear, let me take a detour, okay, and see what is happening physically, and then I will come back to this, okay. So, maybe I will just write it somewhere else. What shall I write? Here I should write that, what is that? Yes, so xa plus minus xb by root 2 when it acts on S2 minus r xa comma xb. This is the result it produces. Okay. Okay, good. So let us take a system of two one-dimensional quantum harmonic oscillators, okay, and they are coupled, quadratically coupled. So if I take just two non-interacting 1D quantum harmonic oscillator, then their Hamiltonian is PA square by twice m plus half m omega square qa square. This is for the first one, plus, so I am taking the frequency, mass, everything same. This is Pb square by twice m plus half m omega square qb square, and they are, of course, they are independent. Okay, so basically you should have qa pb is equal to 0, all those things are there. Right? These are the non-interacting harmonic oscillators, and for that we know what will be the energy eigenvalues, energy eigenvectors, everything. So there will be degeneracy in energy eigenvalues except for vacuum state. Okay. Right. Now let us introduce interaction. Interacting 1D quantum harmonic oscillator. So there the Hamiltonian is again, this will be the case H0 plus, let us say I take it to be half k plus qa plus qb, let us take it to be 2 square plus k minus qa minus qb by, should be root 2 square. So this is again quadratic, and you might ask, and why did you take in this form? I mean, just to make life simpler. This is these are coupled, okay, right. So k plus and k minus are real numbers. Some of them, one of them can be positive, one of them can be negative, something like it.
Did you talk about this two non-interacting?
This is non-interacting quantum harmonic oscillators, and now you take two interacting 1D quantum harmonic oscillator. The interaction is of this form.
I mean, you had some comment on the two non-interacting.
So there we know what will be the energy eigenvalues and energy eigenvectors. So energy eigenvectors will be tensor product of the individual energy eigenvectors, and corresponding energy eigenvalues will be added up, and that will give rise to the degeneracy. Except for ground state, every other state is degenerate here, and that is why I have taken this m and omega same. Right.
But what do you want to study?
Yes.
And from the basic quantum mechanics, I can see the term which is k minus.
Yes.
Qa minus qb whole square by root 2, but the qa plus qb seems.
This is a quadratic one. You could have taken in this form. Where is the problem? You take a quadratic. You take a quadratic Hamiltonian. I mean quadratic interaction. So qa square, qb square, and then qa qb term.
No, I understand.
Hmm.
This is a quadratic, but I'm just trying to think like, what is
Yeah, in the classical case, you have a spring constant which will take the distance square. Okay. See, there is you can take k plus to be 0 also. That is not an issue.
no, but you will keep that term, right?
Yeah, I'll keep that term to make life easier. It's not that it is really needed. Okay. Yes, so what I would like to show you is that the ground state of this Hamiltonian is a two-mode squeeze vacuum state. Okay. And what is its connection with this? Basically, if you apply this two-mode squeezing on this Hamiltonian, you will get this one, this Hamiltonian. And from here, you can figure out easily what will be the wave function for the two-mode squeeze vacuum.
So if just adding two modes squeezing to the first one gives us the interaction Hamiltonian, then the R probably depends on K plus and K minus.
It will depend upon K, it will not be exactly K plus and K minus, it will depend upon that, yes, yes.
So we have all the formulas and calculations. You now want to study the its ground state will be the two-mode vacuum state.
Squeeze vacuum state. No, not just because of that, you know, we want to motivate what will be the form of this, okay, this eigenstate.
Okay.
So, this now I can write as so this part, this is my H naught, the non-interacting Hamiltonian case, okay. I mean, if you look at here, this is what you will get, isn't it? Just this Hamiltonian. This is 1 by twice m P A square plus P B square, which will come from here, and then m omega square by 2 Q A square plus Q B square, which will come from here.
Another reference can be behaves like a non-interacting.
And then you have K plus QA plus QB divided by root 2 square plus K minus QA minus QB divided by root 2 square. Okay? Okay, good. Is it clear? So now I can change these coefficients. So what I will do is m omega square by 2, so plus k, so this is, what will be this? This is 1 plus k plus, and then this will be, no, not m omega square, this is twice k by m omega square, and then this is m omega square by 2, 1 plus twice k minus by m omega square, this is qa minus qb by root 2 square. Is it clear? So I have just, you know, taken into account these two terms. So now you see that, so therefore what I can write is 1 upon twice m P A plus P B by root 2 whole square plus m omega square or let us say m by 2 into omega square root of 1 plus twice k plus by m omega square whole square, then this is qa plus qb by root 2 square. So this is one Hamiltonian, the other one is 1 by twice m ea minus pb by root 2 whole square plus m by 2 omega square root of 1 plus twice k minus m omega square whole square. This is qa minus qb divided by root 2 whole square. So let me call these as, so therefore this is basically h plus h minus. So this is your h plus and this is your h minus, right? Now you see that this modified momentum observable commutes with this one as well as this one. Similarly, this modified position observable commutes with this one as well as this one. So therefore, these are two non-interacting harmonic oscillator Hamiltonian with modified frequencies. Okay. So what will be its energy eigenvalues, energy eigenvectors? Basically, you figure out what are the energy eigenvalues of these energy eigenvectors, energy eigenvalues of these energy eigenvectors, and then take the tensor product. Okay. Right. So so therefore H, I will call it n plus n minus. So these are the energy eigenvalues of H plus and H minus. This will be your okay. So let me call it as h cut omega plus, this is n plus half plus h cut omega minus n minus plus half where n plus and n minus 1, 0, 1, 2, 3, etc. So this frequency, this one with this k plus, you call it as omega plus, and this frequency you call it as omega minus. Is that clear? So this is the basically the energy eigenvalues and energy eigenvectors, right?
What will be the position representation of those energy eigenvalues?
Yeah. So the position representation will be what? Of course Gaussian. For the ground state, okay? Ground state. So the position representation of the ground state of, for example, here if you take 0, 0, so then you can figure out what will be the position representation, right?
Okay.
Yeah. Now the question is, how will I relate the ground state of this Hamiltonian with the ground state of the original non-interacting Hamiltonian? Okay. Okay, so let us look at first the ground state of this Hamiltonian, position wave function of the ground state of this Hamiltonian. Okay. So what will be that? So let me, I will have to take a different notation. Anyway, Okay, so you know the position wave function, okay, wave function of the ground state of H. So this will be, what will be this, 1 by pi to the power half, because 1 by pi to the power 1/4 is here, 1 by pi to the power half, then exponential of minus half. Okay. So I'll have to be little bit careful, because I have expressed it in terms of the dimensionless operators. Okay. So what I should do is I should express it in terms of dimension full operators, otherwise I cannot relate with this. Okay. So anyway, again I'll have to do that. Okay. So for the harmonic oscillator Hamiltonian single mode, so this is let me call it H prime. This is p square by twice m plus half m omega square q square, and so this I know that this is h cross omega by 2 x square plus p square, right? And therefore your x, what should be x? M omega by h cut square root then q. Okay, and your p is 1 by square root of m omega h cut p. Okay, right? So now, so this is your x. So therefore, in order to write it in terms of this one, okay, so what will I do? I will write it as into m, omega is omega plus by h cut, right? Okay, omega plus h cut, and then it should be x is here, this one, qa plus qb by root 2. So this is qa plus qb by root 2 whole square minus half m omega minus by h cut. This is qa minus qb by root 2 whole square. Okay. Is it clear? This should be the case. Okay. Right. Now, do you remember what we have written for this? So basically what you have done here is, so what is your R? You know, the main thing is what is your R. So you see that originally in this case, in the case of non-interacting Hamiltonian, so basically what happened is, in the case of Yeah. So, in the case of non-interacting Hamiltonian, if I want to write, so let me erase this part. So, if I want to write the position wave function for the non-interacting case, okay. So, the ground state wave function of H naught. So, ground state wave function for H naught, because this is just product. So, it will be 1 upon pi to the power half exponential of minus half. So, I should be careful, it should be m omega by h cut, and then this is q a square minus m omega by h cut q b square. Do you agree with me for this one? Okay, this is the ground state Hamiltonian, and this I can write as 1 upon pi to the power half exponential of minus half m omega by h cut. This is qa plus qb by root 2 whole square minus half m omega by h cut qa minus qb by root 2 whole square. Can I write like this? I can. So, what is the difference between this one and this one? Yes. So, omega has been replaced by omega plus here, and it is by omega minus. Okay. So, if I want to connect with this, what I should do is I should write here m omega by h cut, then omega plus by omega. Here I should write m omega by h cut and then omega minus by omega, right. So, what is happening? So, basically this qa plus qb by root 2 gets transformed into square root of omega minus by omega qa plus sorry. So, basically what is happening is this part. So, this qa plus qb plus minus by root 2, it gets transformed into square root of omega plus minus by omega qa plus minus qb by root 2. Isn't it? That is what is happening, and this is what? This is actually squeezing transformation.
But we have only 1 hour, whereas omega plus and omega minus have to be different.
Yes. So, we will have to take it to be in the form that, so I don't know, this with plus it is e to the power plus r or minus r, something like that. So, let us say we take omega plus by omega, square root of that is e to the power plus r. I mean, I don't know whether it will be plus r or minus r, maybe one of that, and then omega minus by omega is equal to minus r. Now, you may say that what is the guarantee that this will happen? Okay, that is of course true. I mean, you can choose this k plus and k minus in that way, that this will happen.
So you are considering this to be the case, or it's
No,
ordinarily-
I choose this k plus and k minus such that these two conditions are satisfied.
No, I mean the square root of this omega plus by omega.
Yeah, this is what, because this transformation I don't exactly remember whether it was, what was that, this xa plus, what was that, xa plus minus xb by root 2 goes to e to the power plus or minus, and that is what.
From there you are.
Yes. Okay, right. So, and this k plus and k minus in your hand, you can choose. So, you choose k plus, so particularly you can figure out from here that what is that? Yeah, so you can. So, this is your omega plus and omega minus, put it there and then you can figure out what will be the case. Okay. So, there will be restriction on k plus and k minus, I agree, but that is okay, because we will have to just show that this will correspond to a two-mode squeezing, right. So, you see that the wave function therefore, for two-mode squeezing is basically of this form, where you can you can now replace it by e to the power plus r and replace it by e to the power minus r or vice versa, right. Okay. So, now look at this, the difference between this and this. What is the difference? The difference is that you have cross term here, QA times QB terms are present here, which was not in this case, and this tells you that the two-mode squeeze vacuum state must be entangled. Okay. Had it not been entangled, then such a cross term would not have been there.
So from a Hamiltonian itself, you can guess that it will be entangled.
Yes, because this is a it's a non-local Hamiltonian, this two-mode squeezing transformation. Okay. Okay. So, therefore, this is our solution that so let me, I'll erase this part.
But in the QA plus QB by root 2 and QA minus QB by root 2, they are tensor product. They don't seem to be entangled in that basis.
Yes, that is true, but if you
The QA and QB basis, then
Yes,
we
yes,
have
yes.
some cross terms.
yes,
But then, like, if you take a state and if you just apply a unitary, that can't, like, just a rotation, that can't generate entanglement.
no, it's a global transformation. This squeezing transformation, two-mode squeezing transformation is a global unitary transformation,
Okay.
and that is why it creates entanglement in general. I mean, this will be more prominent when I write it in the Fock state basis.
Okay.
So, the idea is that if you have cross terms,
Yeah.
that will generally lead to entanglement.
Okay.
Yeah.
Okay. So for the each knot case,
Yes.
you do not get any entanglement, right?
Because it's just a tensor product state.
But here you get for this H case, right?
Yes.
So if you take the variable change kind of thing or change of reference,
Rotation, right? Rotation.
not
From one basis to another basis.
yeah, maybe, yeah, right.
Basis
So
rotation.
there you see that I mean it will be just the Hamiltonian of two individual oscillator, right? For that case,
Which case?
if you consider QA plus QB to be some, let's say,
Yeah, you can go to another frame,
yeah, right.
that is true, but the point is the transformation, canonical transformation that will be required to go to that frame
Okay.
will introduce in general entanglement, okay, because
It's possible because the transformation is just a rotation, right? Can you rotate a state which is unentangled?
no, this rotation is on the two modes together.
It's a global unitary.
It's a global unitary, okay. So, locally of course you cannot, but this squeezing, this two-mode squeezing is a global unitary. So, you cannot write it as unitary on first mode, tensor product unitary on second mode,
Okay.
okay.
But yeah,
So, this transformation that so basically what I am saying is the following, that S2 of R or minus R, we will have to figure out, H0 S2 of minus R, this is your H, okay. I mean this can be minus, this can be plus, that is okay, okay. So, this unitary is a global unitary, okay. So, therefore, although I know the eigenstates of these are what? These are basically your something like this corresponds to NA and NB, right, for this one and that one. But if you apply this S2 of R on that, which will be the new eigenstates of H. So, these are in general not product states, these are entangled states, okay.
No, that is fine, but I am saying that if you go to the frame of that that frame.
Mhm.
So for that case, you see that these are nothing but the sum
Yes,
of-
yes. So you go to a frame from this original expression of H, where you have these, the coupling terms. You go to a frame, that means a phase space, where you can decouple them,
right.
right? And this is possible through this transformation.
Yeah, yeah, that is okay. But I'm saying that in that frame where your coupled one gets decoupled, right?
Yes.
So in that frame, can I say that entanglement is not there?
Of course, this is the point. Entanglement is,
Frame dependent or
see, the thing is that when I write in this, again, where did I write? Maybe I'll just use this. So I have written that H, the original one with the interaction. So this has eigenvectors and eigenvalues like this. Whatever I have written, H cross omega plus n plus half plus H cross omega minus n minus plus half, then this is n plus n minus, right? These are of course product states. In these spaces, these are product states. Okay? But if you want to write in terms of NA NB basis, this is no more a product state.
then entanglement looks like depending on frame or this is kind of. It should not be the case, right?
Like let us say we take a state like just a qubit, qubit system. We just take a state 0, 0, and we rotate the first 0 by UA and second by UB. Then we should again have like.
Yeah, but this is not doing, I am not rotating in A basis to n plus basis and n B basis to n minus basis. I am not doing this. What I am doing is in A n B basis going jointly to n plus n minus basis.
Okay, and what we are saying is that it doesn't have a tensor product structure.
Exactly,
That
exactly.
U is not UA cross UB.
Exactly.
But see, that's not obvious from here, because here we took the Hamiltonian and wrote it in a decoupled form. But yeah, I guess the question is not whether how this Hamiltonian's unitary evolution relates to that, but rather how you go from H0 to H, right? How we go from H0 to H. That is the
Yes.
question.
So as I said, if you check with this, you will get this one. Okay. So now whether it is plus or minus, that one can verify. But anyway, so the question is then, if you diagonalize H0, you can also diagonalize H and vice versa. So the eigenvalues of H0 and H are same, they are isospectral. Only problem is with the eigenvectors. Okay. So the eigenvectors of H will be the unitary transform version of NA NB. Global unitary. And this is what we have called as NA plus NA minus. I mean, there will be some degeneracy, but that's okay. Okay.
Okay, then n plus n minus, as you told that it will be in product form.
This is product form.
Okay. Then H2 since it does.
Okay, so I mean, this is a slightly, this is a complication in notation. This product is in the Hilbert space HA tensor product HB. This is in the Hilbert space H plus tensor product H minus. Okay. So yeah, it depends. The notion of entanglement in tensor product structure is slightly complicated. The division, like in the case of bipartition, it depends upon how you are dividing your systems into subsystems. Okay, so that has nothing to do with physicality of entanglement. When you talk about physicality of entanglement, like measurement, etc., which will give rise to entanglement, there the tensor product structure is fixed. I am not changing that.
Hilbert space to H plus Hilbert space, right?
Together HA tensor HB to H plus tensor H minus.
So state may be product in this entangled in this Hilbert space.
But it can become entangled here and vice versa.
Because you are partitioning in a different way.
Yes.
And here you are doing a different partition. They were separable. Now you are doing a different partition.
Yes.
Not the same partition.
Okay, so similar, can I say that let's say you have a particle. So if you watch that particle from a rest frame, that particle does have the kinetic energy. But if you are on that particle, then it doesn't have the kinetic energy, right?
Yes.
So what can we say? I mean,
Yeah, but
what
that
the
is
absolute thing. I mean,
that has nothing to do with this in this notion of entanglement, because you are dealing with single particle, okay, or single mode of that system, okay, one mode of that system. So that has nothing to do with this. So here, interesting thing comes because you are dealing with two mode system together. Is it clear now? Okay. So therefore, what I'll write here is that, because these are needed for me. You know, I mean, one should be careful whether it is minus or plus. Once you fix your notation, this should be the case, you know, for every time. So this is yeah. Okay. So you see that this e to the power r by 2 factor will not come here, because for one factor it will be e to the power r by 2, for the other one it will be e to the power minus r by 2, right. So they will get cancelled. So basically it will be half exponential whatever I have written here. So this is minus half, I think it should be e to the power r, r or r square, it should be r, yeah, maybe it is r, and then this is xa plus xb by root 2 whole square and minus half e to the power minus r xa, you know, I may be wrong, maybe it is e to the power plus 2r or minus 2r, but anyway, either it is 2r or r, one should calculate properly, okay. So this can be 2 also, I am not very sure, minus xb by root 2 this is square. So this can be 2 here also, I mean, one will have to do it properly. So I think it is 2 here, 2 here, anyway you can figure out, okay. So you see that so this is your the position wave function of two mode squeeze vacuum, right. So all of these are Gaussian, okay. So as we discussed earlier, if I go to the Wigner distribution function of single mode squeeze vacuum or just vacuum or two mode squeeze vacuum, all of them will be Gaussian. So with this I will also write the position wave function of a coherent state. What will be this? This is just displaced Gaussian, okay. So it will be 1 upon pi to the power 1/4 exponential of minus half x minus square root of 2 real part of alpha whole square. Okay, just this, and here there is no question of taking another normalization factor, because this is also normalized, you are just shifting the Gaussian. So now let us look at the Fock state representation or number basis representation. of this is S1R0 and S2R00. And these are bit non-trivial. This is the single mode squeeze vacuum state, this is two mode squeeze vacuum state. So, these are slightly non-trivial. There are different ways of finding out the Fock state representation, but if you want to do it directly, it is a mess, you cannot do that. Okay. So, what there are, so basically what one should look at is this, because for squeezing I told you that the corresponding transformation, at least in the single mode case, is a SE11 transformation. So, you will have to look for its what is called as disentangling theorem of SE11. So, the Iyasawa decomposition that I mentioned last, in some of the earlier classes. So, here also for SE11 you can decompose them into simpler matrices and then you can try to figure out. So, I will not do that. What I will do is I will take a different route. So, what I will do is I will figure out the overlap of coherent state and let us say S1 of R. First for the for the single mode yes.
That is in Fock space or Fock state? The first Fock space is Fock space or
Fock space, Fock state, it does not matter anyway. Basically, I want to write it in terms of Fock states either. So, this is what we want, and for my case alpha I take to be real. I could have taken to be complex, but every time then I will have to write a real part of alpha. So, I take alpha to be real. So, this is a coherent state where alpha is real. So, this I can write as is it clear in the position basis. And now, what is this? 1 upon pi to the power 1 by 4 exponential of minus half x minus alpha whole square, because alpha is real. What is this? This is e to the power r by 2 pi to the power 4 exponential of minus half e to the power r x whole square. Okay. So, this is e to the power r by 2 square root of pi minus infinity to plus infinity exponential. Now, what is the x square term? So, this is minus half x square, this is 1 plus e to the power twice r, right. Okay. And then this is plus x alpha, and then this is minus alpha square by 2. Is that clear? Yeah, it should be clear. Okay. So, therefore, I can take it to be e to the power r by 2 square root of pi minus infinity to plus infinity, dx is there. So, this is dx, then exponential of, see this continuous variable information theory, it requires this kind of integration and all that, you cannot avoid them. So, this into x square, this is plus, so this is minus twice x into alpha divided by 1 plus e to the power twice r. Is that correct? Yeah, it is correct, right? Okay. And then plus alpha by 1 plus e to the power twice r whole square. Okay. Okay. So, this is minus, this is plus. So, therefore, this is alpha square divided by 2 times 1 plus e to the power twice r, and then minus alpha square by 2. Okay. Yes. Okay. So, basically this will be what? 1 minus so what will be this? This is 1 minus. Is that correct? Okay. So, therefore, what you will have is, let me write down here, this is equal to e to the power r by 2 into exponential of minus alpha square e to the power twice r by 2 into 1 plus e to the power twice r divided by square root of 5. Now, this is exact square, right? So, what will be this? This is, so this is basically minus, let us say, beta times some square of x. Okay. So, this is, you can verify, I think it is pi by this quantity. So, this is twice pi 1 plus e to the power twice r. Yes, I think so. Okay. So, this pi will get cancelled. Yes. Anyway, some such thing will happen here. Okay. So, yeah. So, we will have basically root 2 e to the power r divided by, so I can write here like this, 2 e to the power r by 1 plus e to the power twice r, then exponential of minus 2 e to the power 2 r by 2 into 1 plus e to the power 2 r into alpha square. So, this is what the value of this quantity. Okay. Right. And remember, I have chosen alpha to be real. Okay, good. So, I will have to erase some portion. Now, shall I erase this? Okay. Now, let us look at it again. So, I know that alpha can be written as e to the power alpha square by 2, because this is real, sum over n is equal to 0 to infinity alpha to the power n square root of n factorial n, right. So, this can be written therefore as e to the power, this is minus alpha square, sorry, minus alpha square. So, this is minus alpha square by 2, because this is real, and then n is equal to 0 to infinity, this is alpha again is real, alpha to the power n factorial. Now, this is n, S1 of r 0. So, actually this is the term we are looking for, okay, right. Now, you see that this must be equal to this. So, this means that n is equal to 0 to infinity alpha to the power n factorial n S1 r 0, this should be equal to, I will take this e to the power here. So, this is plus r. So, therefore, this is 2 e to the power r by 1 plus e to the power twice r exponential of, so this will be alpha square by 2 here. So, what will be this? So, basically alpha square by 2 minus e to the power twice r 2 into 1 plus e to the power twice r into alpha square. So, this is what? 1 plus minus 1 by okay, so basically it will be, so tell me whether I am writing it correctly. So this is alpha square into 1 by 2 into 1 plus e to the power twice r. Is that correct? I am taking this part here. Something like this, okay? You can check, okay. So now what is it that you can do? This is a series, write it in a series, okay. So this will be 2 e to the power r by 1 plus e to the power twice r. Now it is m is equal to 0 to infinity. This is alpha to the power twice m by m factorial into 1 by 2 1 plus e to the power twice r whole to the power m, right. So what you can see from here is that 2n plus 1 S1 r 0 is equal to 0 for n is equal to 0, 1, 2, etc. So for the odd Fock states, this is always 0, because you know here it is even power only of alpha, because alpha is arbitrary, real but arbitrary. So in order that they are equal, I can choose arbitrary value of alpha, and therefore all the powers should be equal, you know. So this is for arbitrary alpha. So this is what you see, and for the odd even one, you can figure out from here that this is yes, so this is 2 e to the power r by 1 plus e to the power twice r into, this will be, yes, so this will be square root of twice n factorial divided by n factorial, and then it is 2 to the power n, and then it is 1 by 1 plus e to the power twice r whole to the power n. Yes, okay.
So you are comparing by equating the power of.
Yes, because this should be true for arbitrary real alpha, and how that is possible? Only when the, because odd powers anyway is not there, so that will be 0.
Equal to 2m.
Yes,
You can take an integer.
yes, yes.
This is the assumption, or it can be
Why
proved
assumption?
mathematically?
This can always be proved mathematically. I mean, differentiate with respect to alpha, you know.
Oh, acha. Okay, by taking the alpha is equal to 0 or something like that.
Hmm.
You can always equal to.
Yes. Okay. So this is basically these are the coefficients in your expression. Okay. So therefore you know what will be now S1 of r acting on 0. If I write it as n is equal to 0 to infinity, lambda 2n 2n. So what are these lambda 2n? These are your lambda 2n. Okay. I mean, there are nice forms of this in terms of cos hyperbolic, tan hyperbolic, etc., but that's okay. That is what one can figure out. Okay. So similarly, you can also figure out what will be the coefficients for S2 of r acting on 0, 0. So S2 of r, again it will be of this form, n is equal to 0 to infinity, let us say mu n, this is n n. So you can figure out what is mu n, and how will you do that? Do the similar method. So what is it? Basically you take the tensor product of two coherent state for real alpha, same coherent state, and take the overlap with respect to your 2 mode squeeze vacuum state, okay, and use these results and do the same procedure, and you can figure out what are these moments. Okay. So this will be again, you know, it will be something like tan hyperbolic, cos hyperbolic, etc. This will be of course dependent upon r. So here what is it that you are saying? Unless r is equal to 0, all the coefficients are non-zero, and they are, you know, of course correlated. Okay. I am not saying they are maximally entangled, they are entangled. They will be maximally entangled when R is taken to be plus infinity. So, infinite squeezing, which is of course not possible in reality, that corresponds to infinite energy, but other than that this is a highly as you increase R, entanglement will also increase. So, you can figure out the entanglement by, because this is a pure state, you can take the reduced density matrix of individual mode and then find out its von Neumann entropy, that will give you the entanglement. Okay. So, important thing is, if I take the reduced state of this reduced density matrix for individual mode, it will not be a single mode squeeze state, it will be a thermal state, okay, corresponding, and the temperature corresponds to R. I mean, if I increase R, temperature will also increase. So, 2 mode squeeze vacuum state, highly entangled as I increase squeezing, but individual level states are thermal state. Okay. So, there is no coherence basically there. Okay. So, I think I will stop here, and so next time what I will do, I will go back to the Wigner distribution function and talk about the Wigner functions of these states, and then so now we have, this is of course a pure state, this is a 2 mode Gaussian pure state, this is entangled, and then we can go to more general 2 mode Gaussian mixed states, and then we will study its entanglement property. So, this is very simple. I mean, squeezing goes to 0 means this is unentangled, everywhere else it is entangled. Okay, good.